Thank you. Good afternoon, everybody, even. It's a real pleasure to be here. I'm, as I've just been introduced, a materials scientist. I've just started a postdoc, which is what you do after your PhD, if you're stupid enough, in smart materials, and that's what I'm going to be talking about today. Funnily enough, my lab's in this very building just upstairs. So this morning I was battling away with some of these materials, but that means that I'm very happy to be down here and talking to you about them this afternoon. So, materials science, that's a subject that lots of people haven't really heard of. We all know chemistry and physics, but materials science is a bit of a strange one, so I thought I'd first of all just give you an introduction to exactly what materials science is. How do you spot a materials scientist in the street? Well, we've got this Venn diagram here, and it features engineering, chemistry, and physics, which are subjects that we all think we know about. So there's people that work in between engineering and chemistry, and these are the people that tend to work in oil. So you can spot them in the street because they're all evil. Then you've got the people that work in between engineering and physics, and these are the rocket scientists. And these are people that have spent their entire career having their boss tell them, it's not rocket science. Actually, sorry, yeah, it is rocket science. So these people are all really jaded. And then in between chemistry and physics, you've got the ones who invented radioactivity, so they're all dead. And then in between engineering, chemistry, and physics, in the middle of this Venn diagram are the materials scientists. Okay, but what do we actually do all day? Well, we look at stuff. So that could be glass, stainless steel, wood, plastics, ceramics, all sorts of metals, and we zoom in. And we zoom in to see what the atoms are up to inside those materials. And usually these atoms can tell us something pretty interesting about what exactly is going on with those materials' properties. And these properties could be something's hardness, or its flexibility, or its sharpness. So I often describe material science as being like a game of rock, paper, scissors. Okay, hardness, flexibility, and sharpness. Now, I've been telling people this for about 4 months now in my science communication, and I originally wrote it as a joke, but usually most people don't laugh at this joke, which is really annoying, because it's probably the most insightful thing I've ever said about materials science. And I'll tell you why, because rock, paper, scissors is a game that you use to compare materials' properties. So the rock blunts the scissors because rocks are harder than stainless steel, okay? And using this example of hardness, materials scientists, we measure hardness, or rather we display hardness of materials using something called the Moore's hardness scale. And everything can be ranked on this scale. It's from 1 to 10. We actually stole it from geology. So it's ranked from 1 to 10, 10 being the hardest material. Shout it out if you know what that is. Diamond, yes, that's an easy one. 1 is the softest material. Who knows what that is? Talc, very good. Yeah, excellent. And all materials can be ranked on the Moore's hardness scale. So human flesh, sort of close to 1. Fingernails, 2.5. Teeth, around 5. The Moore's hardness scale is why you should never get in a fight with a materials scientist. Because we know what hurts the most. But anyway, this is a talk about smart materials. Now, you will have all heard of smartphones, smart watches. In the future, we're starting to hear about smart fridges and smart homes. But smart materials are a different category. Smart materials are solid objects that have a property, which might be their shape or their color, which changes in response to an external stimulus. So that might be heat levels, or light, or moisture, or pressure, or magnetism. And they do this not using electronics or clever robotics, but actually just because of the intrinsic materials properties that they have. So in this talk, I'm going to be taking you through a whole range of new smart materials. This is my favorite example of a smart material. It's a pine cone. I've got one here. And pine cones are remarkable because they are a natural smart material. I'll show you this video again. So this is a smart material. that changes shape in response to the stimulus of increased moisture levels. And they do this because pine trees have worked out that actually the best weather for planting new pine trees is when it's warm and it's dry. Okay, when it's cold and wet, the pine tree seeds just can't disperse on the wind and plant new trees very successfully. So what the pine cone has developed is what we call a hygroscopic material, and that's this smart material that absorbs moisture and expands. And this hygroscopic material can be found on the underside of all of the pine cone spikes. So when it's cold and it's wet and it's bad weather for planting new pine trees, this hygroscopic material expands, and as it does so, it closes up around the pine cone. Then when it's warm and it's dry and it's good weather for planting new pine trees again, the pine cone opens out and the seeds can disperse. So that's what we are looking at in this video here. And what I really like about this is that it's a brilliant example of a natural smart material. So that's just to prove that material scientists are always just trying to copy nature, as it turns out. But actually, they're not really even a new invention, these smart materials. These are the famous pyramids of Giza. And 4,500 years ago, we built these using a self-healing material. This material was the lime mortar, the kind of concrete-like material that we used to build these with. And it can actually heal itself when a crack develops. So when this material cracks, it's exposed to the moisture in the air and the carbon dioxide in the air. And when that infiltrates into the crack, the material reacts with those two substances to form limestone. And that limestone grows into the crack to completely heal itself. Now, we don't know whether the Egyptians meant to do this or whether it was just a happy accident, but nevertheless, it's meant that, for thousands of years, tourists can come and flock to these amazing structures. And that's all thanks to smart materials. But the first material to be recognized as smart by scientists was much, much later than the Egyptians. It came in 1880, and it was the property of piezoelectricity. Now, it was discovered by Pierre and Jacques Curie, the husband and brother-in-law to, of course, Marie Curie. And they discovered that when you squash a quartz crystal, then an electric voltage is set up across it. And a year later, they discovered that the reverse was also true. When you apply an electric voltage across a quartz crystal, then the material itself physically deforms. Now, when I was reading this, I was wondering, why did it take them a year to discover that the reverse effect was also true? Surely that's just intuitive. But then I thought, actually, if you put a car into first gear and then you put it into reverse, it doesn't start producing petrol. So it's not necessarily obvious that the reverse effect is also true. But nevertheless, they discovered that this was a reversible effect. And this is quite a complicated effect, but I know that we can handle this. So we're going to do some material science and actually find out what is going on at the atomic level that is making a rock be able to produce electricity. So first of all, we have to look at what this material is, and as a material scientist, we would think of this as a crystal. Now, actually, to me, lots of different materials are crystal. Just looking at this desk, this metal would be a crystal. Parts of this hard plastic, probably crystalline. And all that means is that the atoms are all lined up into really neat rows. Now, this is a diagram of a salt crystal. And when we boil it down, well, not physically boil it down, but when in our minds we boil it down to the smallest repeating element that repeats over and over again in these crystals, those are called the unit cells. And material scientists use unit cells to describe these huge crystalline structures. So ordinarily, in most crystals, this unit cell, this repeating unit, is symmetrical. So it looks the same back to front and upside down. But in piezoelectric materials, their unit cell is asymmetrical, so it doesn't look the same back to front and upside down. Now, that doesn't sound that important, but that is actually crucial to how this material works. So when a quartz crystal is just sitting around and it's having no pressure exerted on it, positive charges and negative charges on atoms nearby cancel each other out completely, so there's no overall charge on that crystal. But if we squash the unit cell a little bit, or we stretch it out a little bit, then these atoms move ever so slightly, but now the positives and the negatives can't cancel each other out. So what you end up with is one side of the unit cell that's very slightly positively charged, and one side that is slightly negatively charged. Now, these charges are minuscule. We're talking about charges on electrons here. But if you multiply that charging effect over the millions and millions of unit cells that you have in one quartz crystal, then what you end up with is a measurable electric voltage. And that is what the Curie brothers had discovered all those years ago. Now, this discovery that materials could suddenly start doing things really changed the way that material scientists and engineers and inventors at the time were approaching materials development and materials design. Because suddenly now, materials weren't just things that could have stuff done to them. They weren't just solid objects lying around, but they could actually do useful things for us. And so, since this point, hundreds of new smart materials have been either discovered or invented, and there are millions and millions of patents which use them. Some of my favorites that use piezos, for example, are some piezoelectric crystals that have been embedded under roads. So when cars drive over them, the crystals get squashed. It creates a usable electric voltage that we can use to power streetlights. And this has been trialed around the world already. Another example is embedding them in trainers, so that when we walk around, we create a voltage which we can use to charge a mobile phone. So these are old materials that have been applied to in new ways. But there are lots of other kinds of smart materials that you'll be familiar with. This is my mug that I have in my office. And when you pour hot liquid into it, it changes color. This is a material that physically changes color in response to heat. So we call that a thermochromic material. Some of you might have those sunglasses that go darker in response to going outside. Those are photochromic materials. They go darker in response to increased light levels. So there are lots of examples of these smart materials that we're using today. Those piezos that we met earlier, those were first used in radios, and we all have piezoelectric crystals in our phones and in ultrasound machines and all around us. But I promised you a talk about the future of smart materials. So I'd like to actually start telling this story with a personal anecdote. When I got my degree in materials science a few years ago, I also gained a really scary fear of flying. Looking at our pilot friend over here. I really, really hate flying, and there's two reasons for this. Firstly, I met all the people that were designing the aircraft, and they were all didn't fill me with confidence, let's just say. And also I learned about a lot of physically upsetting facts about aircraft as a materials engineer. My favourite of these is that those turbine blades that you see in the middle of the jet engines, these are operating above their melting temperatures. So we're flying around in planes that should be liquids. I don't know why do we do it to ourselves? And this is very embarrassing for a materials engineer to be scared of flying. But it's also embarrassing sort of from a personal perspective as well, because I have aeronautics in my blood. So you've noticed that I've got a Polish surname. This is the reason why. This is my Polish granddad. He was an aeronautical engineer. He was working as an aeronautical engineer during the Second World War, came over to this country, met my grandmother. Eventually I ended up here. But he was an expert in aircraft design and designing new sorts of wings for aircrafts. Now, this is the reason, as well as my fear of flying, that when I was researching for this talk, I took a special interest in when I read that actually our aircraft that we fly around today are not optimally designed for flight. Okay? Turns out that really the best possible design for an aircraft would look like this. And this is not a very modern drawing, as I'm sure you can tell. This is a drawing by Leonardo da Vinci from the year 1488. And prior to drawing this, he had been studying the wings of birds and bats and flying animals. Because back then he realized that, over millions of years of evolution, because God invented birds and bats back then, the wings were optimally designed for flying, okay? So his design featured rigid wooden components that were flexible and could move, and over those was stretched a very thin sheet of silk. So if you compare that picture of that aircraft to the modern aircraft that we fly around in today, these fixed-wing aircraft, it's very, very different. And materials engineers have developed pretty good, lightweight, strong, and stiff materials like aluminium, which we fly around in today. carbon fibre. But comparing that with this aircraft design, it's very, very different. Now, the reason that Da Vinci's design was so ingenious was that the wing shape could change shape in response to the different stages of flight. So if you've ever watched a bird taking off, you'll see that it puts its wings in a different position to when it's cruising compared to when it's landing. And so this is the ultimate efficient way to fly. But our aircraft don't look like this now. So why not? Well, it's because the materials that we've been working with haven't been up to it so far. However, this is a talk about new materials. So actually, I would argue that smart materials could allow us to go back to Da Vinci's drawing board and make our aircraft that are flexible and sensing and adaptive and morphing and shape-changing that would enable us to actually make aircraft that are a lot more efficient and with less drag than the fixed-wing aircraft that we fly around in today. So this is a mock-up of a NASA picture, which they have drawn to say this is what this kind of shape-changing aircraft might look like. I've since spoken to an aeronautical engineer. Apparently this is not a very good shape for, for a plane, but it gives you an idea of the sorts of smooth wing shapes that we might see in aircraft of tomorrow. So let's meet some of these materials that we might put in such a shape-changing aircraft. And the first of these is aircraft that can make wings change shape. Now, I'd like to introduce you to my first demo of the day, which looks like this. Could I change to the overhead projector, please? Excellent, thank you. Can you see my hand? Woohoo, okay. So this is my demonstration material. It's a spring, a metallic spring. Now, what I'm going to do is I'm going to bend it out of shape. Okay, it's quite stiff. Okay, and look at what happens when I heat it up. Thank you very much. Now, this is a material called a shape memory alloy. And it remembers, literally, its shape that it was in before I'd bent it out of shape. Now, again, in order to understand how this happens, we have to zoom in and see what the atoms are up to inside that material. So if I could go back to my slides, please. Lovely stuff. Now, this is all happening because of something called a solid-state phase transformation. Okay, let's break that up a little bit. The phase of a material is basically the formation that its atoms are in. So examples of phases are solids and liquids and gases, with which we're probably all familiar. But solid materials can be in different phases as well. And all that means is that their atoms are arranged in different ways. So you could have, for example, a crystalline phase that has its atoms in a grid structure, or in a slightly staggered configuration. This is the same material, but just in two different configurations. We also talk about amorphous materials. These are where the atoms are all jumbled up, but we're actually not going to look so much at amorphous, but simply these two different crystalline phases of a material. So in our shape memory alloy then, we start in, let's call it phase one, in this structure where our atoms are all aligned in a grid. Now, the overall shape of that material, we're going to say, is a rectangle. Okay, so that's the shape that we would interact with it on the table. Now, when we deform that material, it stays in that first phase, but the shape of the material changes. It's now this sort of parallelogram type structure. And all of the atoms have moved a very, very small amount, but we would still describe that as being in the first phase. When we heat that material, what it wants to do is it wants to change from phase one into phase two. But if you look closely at those atoms, they're unable to go into that staggered configuration because their neighbour is in the way. So the whole material then, in order to change into phase two, has to go back into that original rectangle shape before the material can change phase. And that's exactly what's going on inside this spring. When it cools down, it goes back into phase one, but it's still in that same rectangular shape. So instead of rectangles, we've got a spring shape, but it's exactly the same thing. We deform it, it stays in phase one, but when we heat it up, it wants to change into phase two. And in order to do that, it has to go back into its original spring shape. So in our smart aircraft then, we could use these shape memory alloys to physically change the shape of the aircraft wings. Now, we'd want to do this because of the different stages of flight and also to decrease drag and to make the flight more efficient. So in Leonardo's design, he had that stretched silk across his wings. Silk is a remarkable material, actually, but it wouldn't be that good for an aircraft. But instead, we could use another smart material called a shape memory polymer. Now, these are relatively similar to shape memory alloys, except they're plastics. And you'll all be familiar with shape memory polymers. This is an example of one. Is it obvious what it is? Oh, yeah, it says it on there. It's hair. Human hair is a shape memory polymer. Now, if I was a biologist, then I would say, you know, hair is made up of all these different layers of cells, very neatly around the core. But as a material scientist, I say, shut up, biology. Actually, what's interesting to us is that hair is made of keratin. Keratin is a polymer. Now, this is a sort of artist representation of a polymer. And in polymers, the atoms are all lined up in really long chains, molecular chains. And these chains generally are all kind of higgledy-piggledy. And in between those chains, you have bonds, which hold the whole material together. Now, in this diagram, I've got strong bonds, which are those solid red lines, and weak bonds, which are the sort of dashed lines. Now, I'm sure there are some nerds in the room, so you'll be happy to hear that the weak bonds are hydrogen bonds, and the strong bonds are disulfide bonds. But the important thing is that some of them are strong and some of them are weak. Now, if anyone's ever tried to change the shape of their hair temporarily using heat, you'll be familiar with what is going to go on here. So when you heat your hair above exactly 144 degrees Celsius, what you're doing is you're breaking those weak intermolecular bonds, the bonds that are holding those chains together. And once you break those weak bonds, you can manipulate the hair and get it to physically change shape. When it cools down, those weak bonds then reform, and your hair is in now a temporary new shape. If you get water on it, then that water will break those hydrogen bonds, and the hair will remember its previous shape because it's pulled back by the strong bonds into its original shape. So again, this is a shape memory effect because the material can remember the shape that it was in before you put it temporarily out of shape. Now, anyone who's ever tried to permanently change the shape of their hair, either using a perm or a chemical relaxant, what you're doing here is you're not only breaking the weak bonds, but also the strong bonds as well, which is why hair products sometimes smell quite sulfurous, because if you remember I said that was a disulfide bond. When you break those strong bonds, you end up releasing sulfur, and when you want to put the bonds straight back in, you have to put more sulfur in. So that's just some fun hair facts. But we could use very similar shape memory polymers in our shape-changing aircraft, because shape memory polymers would be able to be both flexible in order to allow for the changing shape of the wing underneath, but would also be able to be strong and stiff in order to withstand the aerodynamic forces. But I've been talking about changing the shape of materials using heat. But as I'm sure many of us have been aware, when you go up into the atmosphere, it gets very, very cold. When you fly to countries that aren't the UK, it's sometimes quite warm. So now, where was I? Yes, we need to control the temperature of our smart materials very, very closely, because if we don't, our aircraft might get effectively a dead leg, or it might start to move when we actually don't want it to because of the atmospheric temperature. So there's one example of a smart material which we could use in order to very closely control the temperature, which is this. Now, sorry, I've made you be very busy today, James. If we could go back to, yes, brilliant, right. Now, can you all see that? This is a very boring black liquid. Oh, it's reversed. There we go. Very boring black liquid. What you're seeing in there, that circle in the middle, I think is just a reflection of the light more than anything else. But look at what happens when I put a magnet underneath it. Can you see that? Now, it looks quite solid, but actually I can mess around with it. It feels completely liquid to me. Okay, it flows around. Now, this is a material called a ferrofluid, and it's really very beautiful. And this is a liquid smart material that changes shape in response to having a magnet near it. And ferrofluids were invented actually by scientists at NASA in the 1960s because they needed to try and control what their liquid fuels were doing in the gravityless environments of space. Because, sorry, if we go back to my previous slides, liquids do very strange things in space. This is a video of ferrofluid doing its thing. It's pretty beautiful, telling the time. But yes, liquids do very strange things in space. This is an image of astronaut Chris Hadfield simulating crying in space. Obviously, because he's a male astronaut, he's actually not allowed to cry on camera in space. If you watch the full video, he just squirts some liquid into his eye to simulate crying. But this shows the really weird surface tension effects that you end up with liquids in space. And this is the reason that NASA wanted to control their liquids. But for us, in our aircraft, actually what we'd want to do is to control the temperature. Now, this ferrofluid contains nanoparticles of magnetic nanoparticles, rather, sorry. And because they're magnetic, they are metallic, and metals are really, really good at conducting heat. So we could physically pump this ferrofluid through the wings of our aircraft, almost like veins, in order to precisely control the temperature of those moving smart material components. So our aircraft wouldn't end up changing shape when we didn't want it to, which we can all agree probably is a very good thing. So I've shown you some smart materials today, my shape memory alloys and my ferrofluid. Why aren't we all flying around in aircraft like this already? What's going on? Well, it turns out that there's quite a lot of problems with smart materials. And funnily enough, these problems are also quite similar to those of our favourite politicians. Some of them are too slow, can be quite unstable. Their performance can diminish over time. They can be difficult to control. Some of them are toxic, not very good for us. Some of them are quite expensive. But these problems are not too difficult for material scientists and engineers to solve. We're quite used to solving these kinds of problems with our materials. So it's my prediction that within the next 20 to 30 years, we will start to see these kinds of smart materials start to infiltrate our daily lives. And we might even start flying around in these amazing new smart aircraft, which I think would be very exciting. So I'd just like to finish on a couple of final thoughts on materials science, which is that although it's a subject that not many people have heard of, it is relevant to all of our lives. Okay, as human beings, we love materials. We have opinions on them. We furnish our homes with them. We buy them at great expense sometimes. And so we have emotional connections with materials. But what I wanted you to take away from today was that the next time you come into contact with a material that you think looks quite boring, if you've got an appreciation for the material's properties that that material has, for example, it might be lightweight and flexible, it might be see-through, it might be, I don't know, flexible like this sheet of paper. If you've got an appreciation for those materials' properties, and you start to appreciate exactly what it is that the atoms are up to inside those materials, you're not only gaining appreciation for the world around you, but also for the nature of atoms and therefore the nature of the universe. And I think that that is something pretty special. So that's where I'll end. Thank you very much for listening.